Hello, class. Can everybody hear me? Is my audio coming through?
Yes, sir.
Thanks. Now, I want to make an announcement. We're going to have our first test next week, and it's actually going to be a Blackboard test. It'll be similar to your WebAssign problems, and also if you look at some of the practice tests, which are some old tests that I've given in this class, it will resemble those. So the types of problems you're doing on WebAssign, you'll actually do on your test. And as you look at those problems, you'll see many similarities to what you're doing with your WebAssign and the lecture notes. Now, I did get an email about the cross-section method, and I wanted to make a comment about that. What I did last week was I posted a video on the cross-section method because it's really not as complicated as the more applicable disk and washer method and the shell method that we did last week. So let me just share this with you so you can see this. Some of you have actually watched the video. I think there have been 8 viewers. So what I did in the video is I basically went through the cross-section method, and I actually talked about a standard method. All of these methods are written up in the notes, also in the lecture notes, so that gives you an extra source of information. And also the PowerPoints that are posted are good just for summaries. But I went over the method for actually solving for the area of a square pyramid. The idea is that we will have a simple cross section that is perpendicular to an axis. In most cases, the x-axis, in this case, the vertical axis. And so please go through those. I think you'll find the video very straightforward. But I did have a question about the cross-section method from 7.2. So what I did, again, if you look here in the video, I do 2 of the problems from problem 10 in your WebAssign. So I'll work these out and show you how to do them. And again, it's a very simple procedure. So that's why I did the video, so you would have that information. But Hugo actually asked about a problem here, and I've set this up. Let me share this with you. This was the first problem in number 9, and it really depends on how your problems are generated in WebAssign. So here's another example, and so I thought this might be a good one just to have for you to review. In this case, like in the problems that we did before, the base was actually a circle. In this case, the base of the solid is bounded by these 2 curves. So the base really is what depends on what the given information is. With the square pyramid, the base is a square, and the cross sections perpendicular to the y-axis or vertical axis are also squares. But I thought this was nice because it was more like the area problems. So when you have a curve y equal x plus 3 and a curve y equal x squared minus 3, that's just a linear equation and a quadratic. So what you do is you treat this like an area problem, and then you say, okay, where's the intersection? So we set the ordinates equal. So this is all reviewed that we've done before. Now, what happens is that the cross sections are squares and they're perpendicular to the x-axis. So we can simply take the area measurement here, that is the upper curve minus the lower curve, to get the actual edge of the square. So the base is what gives you the geometry that you need. Now, again, this is all predicated on the fact that you have a cross section whose area you understand. So you can make up your own solids. You can construct your own solids to have cross sections of your choosing. That's why this is a very nice and simple method. Engineers like this. If you're an architect, maybe you want to have a building whose cross sections are circles. I mean, you can do anything you like. And so now the edge is this. Now, one of you asked about a question in the washer method where we had this, unfortunate situation here where you basically have to square a trinomial. And that's not hard to do, but again, when we look at the area of the cross section, it's just an edge squared. And so this is the twofer type squaring. You square each of these to get x to the fourth, x squared and 36, and then you go by pairs and hit them with twos. That's the twofer method. So you get a negative x cubed times a 2, and then you get a 6x times a 2, and then you get a negative 6x squared times a 2. So that generates all of the elements of this trinomial expansion. We're not used to that. We just like binomials. And so when you collect your terms, you get this. And so what I did is I went ahead and set this up. So now we actually integrate the cross-sectional area from the interval of integration, which we concluded here when we found the intersection. And so we go from -2 to 3 this, and that's just a standard integral that you can work on. Now, I worked this out, and I want to see what you get. I worked it out by hand, and of course, you're going to get a lot of messy arithmetic because the lower limit's not 0. So that was like, wow, what can we cheat here? No, we don't have any symmetry. But so this is basically what you have to do. In the video, we talk about examples where the base is a circle. And so you can get the actual dimension by subtracting the upper arc from the lower arc to get twice. So the length of the edge is this way. So these might be a little bit more straightforward, but certainly the same concept involved. Here, the cross sections are equilateral triangles, and I actually do a little derivation for the area of an equilateral triangle. You don't have to do that. You can just use regular trig, but I thought since it's a 30, 60, 90 triangle, we can do that. And then of course here we have semicircles, so it's just half pi r squared. So again, this method is dependent on the cross section, knowing the cross section and knowing the area. So don't look at this as being difficult in the sense of the shell method or the disk method. Those are much more complicated and easier to apply in more general settings. This is a very specific setting. So I just wanted you to get a short introduction to this. Nothing major, just enjoy. Nothing that like, oh wow, I've got to spend hours and hours on this. So that's why I made that video. So if you haven't done the video, please go ahead and look at that. Now I'll cheat. I did get an answer, 625/6, so you can check that out. Now the topic for today is going to include some information about arc length and surface area when we can actually generate a surface. Now, when we actually do the problems with the shell method and the disk method, washer method, we generate a solid. And we might be thinking, what about surface area? Well, in the more general case, it's pretty difficult. But what I want to talk about right now, we'll do several examples today, is arc length. Now, in your actual notes for the class, you have some of these motivations and all, and I want to just give you the elements of this. And if you want to read more about the frustum and you want to read more about the application of the mean value theorem, you can use my handwritten notes for that. But I wanted to just go ahead and take some time today to talk about these methods and then do several examples to give you some computational experience. So what we have here is we've got a curve y equal f of x, and we'll just take an interval of integration to be a to b. And what I've written here is C1. This is a little bit new, and I'll do like we do in college algebra. so you can just kind of see what I want you to copy right now. When we say C1, we mean that the actual derivative of f is also continuous. We need a nice function. So C, lots of times you deal with functions that are C infinity. That is, they have continuous derivatives of all order, like polynomials and, and nice exponential functions. So we need this. Now, when we talk about length of a curve, that becomes a calculus statement. For instance, the length of a curve where x runs from A to B is going to be Pythagorean in the sense that we're going to use the Pythagorean theorem to approximate tiny subinterval lengths, just like we do in a Riemann sum. And when we actually apply the Pythagorean theorem, we're actually summing this radical over the interval A to B in integration. So when you look at this, you see it is Pythagorean. That is, we actually have to integrate the square root of 1 plus the derivative squared. And then we're thinking, wow, those integrals are in general difficult, because when it comes to a Pythagorean integrand, we've already seen with the inverse trig formulas that those are special patterns, and they are not very user-friendly if you can't get the integrand to meet that pattern. And if you can't, then you've got to use another method. And we're going to find when we do trigonometric substitution, that'll be another method that we can use, or maybe inverse hyperbolic, which you would have talked about in Calculus 1. But if not, that's okay. The story behind these types of integrals is very voluminous in analysis. And when the powers change, you generate elliptic integrals, as I've said before, and elliptic integrals can be very daunting. So we're going to start with these, and then as you get more sophisticated, you will probably use some of these in your more advanced engineering classes. So now, basically here, this integral will require that we take the derivative of the curve. This is our bookwork before. We square it, add 1, then take the square root. So you're thinking these better be some special functions so we actually end up with something that we can actually integrate. So when I test you and we do examples of this, they will definitely be integrals that you can compute. So don't worry about that. You won't have to pull out Simpson's rule or the trapezoidal rule to be able to do these. Now, what I want to do is now do an example of this. So we'll wait on the surface area. Now again, the calculus classes are full of computation. Not necessarily difficult, but sometimes long computation. So let's say we are interested in the following curve. We have y equals 2/3 x squared plus 1 to the 3/2. And x, this is tailor-made. X lives between 0 and 2. And what we want to do here, ladies and gentlemen, is compute the arc length. So in your problems, in your WebAssign, they will direct you to say, compute the length of the curve. Now, again, lots of times when we refer to length, as you saw in the formula, we call that a lowercase s. That's become conventional. Good or not, it is what it is. So if we recall, the arc length, let me just write that again, will be A to B. And since we're given y, we'll just write y in the formula if you want. You can write f, you can call that f of x if you like. 1 plus y prime, quantity squared, dx. And so now, just like the quadratic formula, don't do all of this under the integral sign, do all of this to the side. So let's go ahead and do the bookwork here. Y prime, it's kind of like setting up a solid of revolution. So we're going to do what? 2/3 times 3/2 by the power rule, x squared plus 1 to the 1/2, subtract 1. So this will give us x squared plus 1 to the 1/2. Now, when we're doing these types of problems, oh, and I'm sorry, Professor Ron gets -5. We need the chain rule. That's one good thing about math, it's self-correcting. So, chain rule. So now when we look at this, if we think about what has to go later, we think about the following. That is, we want to square and add 1. So this implies 1 plus y prime squared will now be 1 plus, so we square the 2x, we get a 4x squared. And if we square the radical, we're relieved of it. Now, again, these are tailor-made to work out, so don't look at this and say, oh, I'm cooked kind of thing. So let's go ahead and expand this and see what we get. So we've got what, a 4x to the 4th plus a 4x squared plus a 1. But we know if you were taking your college algebra or algebra 2, you'd say, well, that's a perfect square. Remember, the perfect square looks like this, a plus b. That's what we want to write, but what does it look like on the other side? A squared plus 2ab plus b squared. So here we see that a, in this particular case, is 2x squared, and b is 1. So we square it, we get that, of course, and then 2 times the product is this, and then 1 squared. So this is the perfect square, 2x squared plus 1. So what we're doing when we work with these types of problems, unless it's a nice chain rule, table ready form, we'll usually have some occurrence of a perfect square that makes computing the radical of this very simple. Okay, so again, look for this. These are special type functions for now, so you can move to the next level, even though some can get pretty tedious with just basic mechanics. So now this implies that the arc length, and we're given the interval of integration, will be 0 to 2. So we take the square root of the perfect square. So now the square root of the square is the absolute value. We know that from, well, probably not algebra 2, probably college algebra. But now, of course, when we look at this particular function on 0 to 2, it's always positive. It's never 0 to be exact. So we can remove the absolute values. So again, we're like, wow, with a little bit of algebra here, we have a very simple integral. So the idea with these types of problems is do this in steps, just like you do an integral. Look for a pattern, say work out the integrand, then you can apply the radical here in a clean way. You know, unfortunately, if you don't try to break things down into steps, it's hard to go back and find errors. So if you break everything down nice and neatly, you forget the chain rule, you're like, whoa, wait a minute, chain rule. It's easier to go back and check. So now add 1 divided by the new power. So we'll get 2/3 x cubed plus x. So now, of course, we have our good friend, the lower limit of 0, which annihilates this. So again, when we have it, we're happy. So this gives us 2/3, 2 to the third plus 2. So this will be a 2/3 times 8 plus 2. So we have 16/3. And if you will, let's go ahead and write this with a 3 in the denominator. So this is 6/3. So that'll give us 22/3. Now, again, the technique for arc length is essentially a calculus problem, because we know how to find the length of a segment. That's Euclidean distance. That's Pythagorean. So we apply Euclidean distance, that is the Pythagorean theorem, to intervals from the partition. And then that approximation becomes exact when we let the norm pass to 0. So that's why we have the square root here, because it's Euclidean distance, it's Pythagorean, but what's built into this is the mean value theorem. If you take me for Calculus 1, you treasure the mean value theorem, because it is the fundamental theorem of differential calculus. We like the chain rule too, but without the mean value theorem, it'd be like us trying to do complex analysis without the geometric progression. We'd have to really find some really nice tricks to do the work. Now, let's look at another one. I want us to get a little bit of practice with this so you're comfortable with the computation. And I want to spend, like I say, I want you to understand how things come about, but I also want you to have enough time to compute to feel good about the algebraic part. So here's another problem of interest, which will allow us to use a lot of our Calculus 1. So we have an interesting function here. And again, I draw my lecture examples as you look into the notes from the WebAssign problems. So this, again, is to help you out, to give you new ideas that you can apply to what you already know. So we have the natural log of cosine of x. That is our function. And x lives here between 0 and pi/4. So we have a nice argument here. That is, the argument cosine is positive for this interval. And so, of course, this is defined as we need it to be. And so what we want to do, again, is get some practice with this. Compute arc length, or compute length of curve. Again, arc length. Why we like the S is that, for instance, with the differential, we'll say ds, the arc length differential, we can write this way. And we can use y prime or f prime, it doesn't matter. If the independent variable is x. So the physicists love this. They just say element of arc length, element of arc length. Like I say, the ideas here are very user-friendly, because they take all the concepts you learned in Calculus 1. So now, remembering the element of arc length, we need to compute that first. So let's go ahead and do some differentiation here. So remember from Cal 1, the derivative of the log function is the reciprocal of the argument times the derivative of the argument, the good old chain rule, the negative sine x. Now, when you actually compute this, sine over cosine is tangent, so we get the negative tangent. You know, You learned everything you needed to know for calculus in college algebra and trig. So that's all we ever use. And we go back to the basics every time. And if we make a mistake, it's a basic one. That's just life, that we're human. And so never tire of the fundamentals. So now we want 1 plus y prime squared. So this will be 1 plus negative tangent quantity squared. So this will give us 1 plus tangent squared. Now, of course, we know this is to beat the horse to death. I'm sorry. This is the Pythagorean identity. 1 plus tangent squared is secant squared. That's our friend. We'll use that a lot in the sequel. Okay? So again, this is kind of fun because you get to review all of your concepts from Calculus 1. So now, by definition, S, the arc length, will be the integral from 0 to pi over 4. And now we take the square root of the 1 plus y prime squared. So we have this. And of course, the square root of the square is the absolute value. If you square the radical, you just get the radicand. There's a difference. There's a big difference. So now, again, the secant function is the reciprocal of the cosine. The cosine is nice and positive here, so its reciprocal is also. So now we can relieve ourselves of the absolute value since the secant function behaves like the cosine function over that interval. Okay, so now this is a calculus 1. What would we do in cal 2 without cal 1? We're not using anything but cal 1. And this is a standard integral by Lagrange. This is the natural log of secant x plus tangent x. That's the antiderivative. Let me go ahead. I think I didn't write this in red here, but maybe I should have. Let me just say, recall. This is one of your standard integrals. Secant x dx, this is a du over u, is the natural log of the absolute value of secant x plus tangent x plus an arbitrary constant. So very, again, just what we learned in Cal 1. So we'll apply that antiderivative. So we have the the absolute value natural log secant x plus tangent x, 0 to pi over 4. Like I say, there's so many pieces here, and that's why we want to get as much practice as we can. So now we'll just go ahead and apply the fundamental theorem. So we have natural log of secant of pi over 4 plus tangent of pi over 4 minus natural log, and we'll have secant of 0. Now, of course, WebAssign always puts in the additional parentheses that you close, but that's not ambiguous here. That's secant of 0 plus tangent of 0. Now, the zeros look a little bit awkward there. I don't want you to think I'm writing an O or something, so I'll go ahead and put that in, but here it's clear. The pi over 4s have a little bit more presence than the 0 does. Okay, so we have natural log. Now, of course, secant of pi over 4, that's going to be the reciprocal of the cosine. So again, we can just write this as 1 over cosine pi over 4, if you like, since that's what everybody remembers. The tangent of pi over 4 is just 1. And I'll write this as cosine of 0 since everybody's more comfortable with that. And of course, tangent of 0 is 0. So now cosine of pi over 4 is 1 over root 2. So when we reciprocate, we get square root 2. Now, of course, cosine of 0 here is, well, of course, we don't want to cheat. 1 over cosine of 0, cosine of 0 being 1, 1 over 1 is 1. So of course, now we just have the natural log, and of course, this is a positive argument, so we are relieved of the absolute value. And then of course, we have log of 1, which is 0, so this gives us natural log of the square root of 2 plus 1. Now, I like the exact answers, and so if WebAssign says approximate, fine. You get the exact answer, then you approximate it. There are hiccups at times. I'm sorry about that, but they are few and far between with the WebAssign. The WebAssign is a great tool, but just remember that if you're working a problem, work it out exactly, and then approximate the exact answer. And if you have any issues with that, just send me a message on the WebAssign, and I'll be glad to look at it. Again, we always want to work for an exact response. As you do science and engineering, of course, there'll be times when you'll need to approximate things, but you want to do it in a way that you preserve the mathematics and don't enter unnecessary rounding, which can ruin the mathematics. So let's try one more. Well, we're actually going to do several, but I want to make sure you have this down well. And then when we actually work on the surface area, we'll just basically tack on using the area of a frustum, which is basically just the waste paper basket, tack that onto the Pythagorean element of arc length, and we'll have a surface area formula. So again, the geometry will be with us, so to speak. Now, what I wanted to do here, this problem I actually have written up in your lecture notes. It's a good example because it really harkens back to the calculus of the natural logarithm, and we need that. So that's why I like the WebAssign. The Larson book has really good examples and good problems, and it's worth your time. So we have y equals the natural log. Now this is going to remind you of the hyperbolic functions. So we may say a little bit about that. You can use any kind of mathematics you want to solve a problem as long as it's consistent with the problem. So here is another interesting function. We have the natural log of e to the x plus 1 divided by e to the x minus 1, and we live on the interval. That is, where does x live? From natural log 2 to natural log 7. And that preserves a positive argument here. So this is well defined. So we'll just say x lives here. Let me write that in. So that's where our x lives. And again, we want to compute length of curve. This is a good calculus example in the sense that we review a lot of nice calculus. So yeah, the WebAssign can be deceiving when you see problems like this. Now, of course, we need the element of arc length. I thought this was good because this can be done many ways. Remember, an identity is an equation that is true for all values of the variables for which it is defined. So we're thinking, well, we could reciprocate this and then use the quotient rule, and we're thinking, no. I try to teach my Calculus 1 kids to go ahead and use the identities of the logarithm and hopefully make a simpler derivative. And of course, because the identity equation is valid where it's defined, we'll get the same answer. It'll be equivalent. So now first, let's say, okay, we're going to be lazy and break this down, the log of a quotient, into the difference of logs. Of course, when we have sums as arguments, we need to use the parentheses so we keep up with what we're doing. So this just basically utilizes the log of a quotient as the difference of logs. Okay, so we use what we know about the logarithm. So now y prime, now we can be lazy, so to speak. We'll have 1 divided by e to the x plus 1 times the derivative of the argument, which is e to the x, minus 1 over e to the x minus 1 times the derivative of the argument here, which is e to the x. So what I did in this particular case is I just got a common denominator and cleaned it up a little bit. So we need this factor and this factor, which is actually a difference of 2 squares. So we have to do a little bit more work to make this look nice. We want to set it up for a nice integrand. So again, here, notice we don't have this factor, so we hit the e to the x here with the e to the x minus 1, just basic algebra. And then we have minus here, so we hit the e to the x with this factor, e to the x plus 1. So now we go ahead and expand e to the 2x minus e to the x. Now we have minus e to the 2x minus e to the x. And then if you will, and this is fine here, notice this is just a difference of 2 squares, so we can write this as e to the 2x minus 1 for now. And now, of course, the square terms absorb, and we're left with the negative 2. Negative 2 e to the x. So negative 2 copies of e to the x, e to the 2x minus 1. So that's our y prime. So you look at this and say, well, wow, this is plenty of work here. So at least we have an expression that's usable and it's nice and tidy. So now this implies that we want 1, well, that we can actually compute 1 plus y prime squared. So if we know y prime, we know what this will be. So we get 1 plus, so we're going to square this. So let's write the square. So we get 1 plus 4e to the 2x divided by e to the 2x minus 1. Now, if you look at this and you think about, okay, it would really be nice if we could make this a nice perfect square. So at this point, what we want to do, and of course we need to square this, what we want to do is get a common denominator and see what we can make this into, hopefully something useful that we can actually integrate. So now we'll get a common denominator. So we have e to the 2x minus 1 quantity squared. So that's what we need here, e to the 2x minus 1 quantity squared plus a 4e to the 2x. Save a little bit of room here, get rid of some of that fraction bar. So now let's expand this. So we get, and this, and I'll say when we work with these types of problems here, notice we've just ended up with binomials, no trinomials to square. So we get e to the 4x minus 2e to the 2x plus a 1 plus 4e to the 2x. E to the 2x minus 1 squared. You're thinking, well, why did you put this problem in the WebAssign? I could just give you easy problems and then you wouldn't learn anything. So we do these problems so we can get better at our mechanics. So now notice this is, hopefully we've got our fingers crossed, we're going to get another perfect square. So we get e to the 4x. And now, of course, we have 2 copies of e to the 2x. And then we have the 1. So again, we have another perfect square. Remember, an identity is an equation that is true for all values of the variables for which it is defined. We use them without thinking about it. So now, if you like, our A is e to the 2x. So we're just doing algebra here. Algebra 1, algebra 2, right? E to the 2x. And b is 1. So that's a perfect square up there, just like before. So we get e to the 2x plus 1, a plus b quantity squared, divided by e to the 2x minus 1. Now, if you will, you can go ahead and write this under the same umbrella, using the fact that now we're using an identity. Laws of exponents. Okay. So what we've managed to do here is to create an integrand that's user-friendly. So we look at this and say user-friendly. So I think what you're going to see here with these types of problems is that when it comes to working on ArcLink and just in general applications of the definite integral, we just have a lot of bookkeeping. It's like we've become court reporters. So now we can apply the definition, again, the definition of ArcLink. So this gives us S equals the integral from log 2 to log 7. I've written kind of large, so I have to move to another sheet of paper. So we're going to have the square root of e to the 2x plus 1. That's e to the 2x plus 1 divided by e to the 2x minus 1 squared square root. So now, of course, this will be the absolute value. E to the 2x plus 1, e to the 2x minus 1. Now, and what I've written here, and this is somewhat important, when we put the log here, for instance, and we think about what we're doing, it's important to notice that this part of the integrand is always positive for ln2 to ln7. And so again, you can substitute your ln2 and then move the power, the 2 up by the power rule, and basically have e to the ln of 4, which is 4. So again, that for all of these, this interval of integration, this denominator, clearly the numerator is positive, the denominator stays positive. So we are relieved of the absolute value. That's just a little analysis we do to make sure, can we get rid of the absolute value, which we can. Again, using the logarithm identities. I mean, you could just forget doing all of this and throw caution to the wind and probably get lucky, but it's better to know that it's correct. Now, this is where I want to help you out a little bit, because at this point, we have a little issue. And when I actually worked this problem out, I thought, okay, I need to use a hyperbolic function, because right now, if you thought about trying to do this with calculus, you're thinking, well, you know, we could do like a du over u bit and try that out and see what happens. But the problem is that +1 there, that's in the way. So it won't work. So we want to convert this to a nice hyperbolic function. That's why I did this. And if you don't remember the hyperbolics, you should have done this in Calculus 1. I'll give it to you now. So here's the trick, and I wrote this clearly here. We're going to multiply by a convenient factor of 1. So here's what we're going to do. And then I'll give you the essence of the formulas that I'm using. So we have e to the 2x plus 1, e to the 2x minus 1. And so we're going to multiply and divide by e to the negative x. That's going to put our integrand into a form that we actually recognize. So we have ln of 2, ln 7. So again, just put your parentheses here. So this will give us e to the x plus e to the negative x. And then of course here we get e to the x minus e to the negative x. Now this is where I need to give you a little bit of understanding here, and this is important. This function right here is the hyperbolic cotangent, and that's an easy integral. To make it a little bit simpler here, and of course that's why we use Larson. So this equals the hyperbolic cotangent. It's cotangent with an h, the h for the hyperbolic. And so this is a standard integral form from Calculus 1. And again, you could do this with a du over u. And let me go ahead and put this in. The antiderivative, again, this is du over u. That's how you do this. I just want to go ahead and give you this formula. Is the natural log of the hyperbolic sine plus a constant. I'll fill all of this in. I'll give you the definitions of the hyperbolic sine too and cosine. So this will be natural log hyperbolic sine integrated, or actually evaluated from log 2 to log 7. So let's go to the next page. So I'll just move this up here and add another page so you can see what we're doing. Now, the hyperbolic sine can be written this way. E to the x minus e to the negative x divided by 2. So that's the definition of the hyperbolic sine. Now the beauty of this and what makes all of this work is that this is positive on this interval of integration. So let me just give you some simple definitions here. We'll finish the problem over here. The hyperbolic cosine, and you can do these like regular trig. If you know cosine and sine hyperbolic, you can do the tangent, the cotangent, hyperbolic, all of those just like regular trig. This is e to the x plus e to the negative x over 2. And as engineers, future engineers, you will use these hyperbolic functions. E to the x minus e to the negative x over 2. So this gives us the definitions of the hyperbolic cosine and hyperbolic sine. So now we can substitute here. So we're going to have natural log. I'll go ahead and work all of this out. E to the log 7 minus e to the negative log 7 divided by 2. And then we'll have minus natural log. Again, this is positive, so we can relieve ourselves of the absolute values on this particular interval. We'll have e to the ln2 minus e to the negative ln2, all divided by 2. Okay, so I'll move this up, and then we'll come back to it. And I just want you to see how we can use the laws of the logarithms here. So not skipping any steps. So you get some nice pre-cal review. So now notice here, this is just plain old 7 because these are inverse functions. And now, of course, the negative here will move up to 7 to the minus 1. And that'll just give you minus 1/7. Again, e to the negative ln7 is just e to the ln 7 to the minus 1, which is 7 to the minus 1, which is 1/7. Okay, so just some basic pre-cal divided by 2. And now here we'll do the same thing. We'll get 2, and again, like we have 1/7 here, we get 1/2 here. This is a really elegant problem. Lots of nice mathematics going on here. And so we have ln. So let's get a common denominator of 7 here and collapse it. So we'll have 49 minus 1 divided by 14 minus ln. So we'll have 4 minus 1 divided by 4, collapsing the fraction. So we have ln of 48 over 14 minus ln of 3 over 4. You don't need the parentheses if you don't, and I'm spacing this out so you can see the arithmetic. So here, if you like, we can divide here by 2. So we have ln 24 over 7 minus ln 3/4. And then, of course, we have the log of a difference of logs, which is the log of a quotient. So we have 24 over 7 times 4 over 3. And of course, the 3 absorbs into the 24 to give us an 8. So we have 8 times 4 over 7. And you get log of 32 over 7. So the calculation here, again, this was more of a exercise in reviewing calculus. So you can use your ebook. That's why we like the WebAssign and go into chapter 5, section 9, and look at the hyperbolics. That's what I teach at the end of Cal 1. And it's a nice treatise on the hyperbolic functions. And so you'll see these definitions here. They're really easy to work with. The beauty of the hyperbolic functions, they act like regular trig functions, but we have these beautiful formulas for them. So we can really understand their calculus because we know the calculus of the exponentials. But the standard trig functions are much more abstract. We base their definition, at least initially, on geometry. And so it's much more abstract and more difficult, really. So again, when we think about this problem, we think about constructing the 1 plus y prime squared to get a nice integral. Then we utilize some information about the hyperbolics. Again, you can use the du over u here if you like, but I thought it would be nice to introduce this formula that you can use, put on your note cards. And then we basically analyze. And of course, if WebAssign would like an approximation, you can approximate the final answer because you have an exact answer. Okay, so the idea here is that arc length is fun. If you take the time, like I say, I will only test you on problems where you can actually produce an integrand that you can actually integrate. And that's the key here. The idea is that as you get more experience with the techniques and integration in this class, we can be a little bit more free with what we have here. Some of the most simple curves from college algebra, when you apply the arc length formula, give you Pythagorean integrands, which require trigonometric substitution, at least as one method to do them. So not a trivial problem at all. And even when we can do it, we're finding in this problem, there's plenty of algebra to be done. Okay, we'll do some more of this. But now what I want to talk about, and of course, when you practice this, you go back and do the area problems in the cross section and what we've done before, and they seem easy. So that's the nice thing about the arc length. Now, there are lots of really good examples in your WebAssign, but I want to go ahead and say a little bit about the frustum. Now, and of course, there's more detail in your lecture notes, and that's fine, and you should look at that if you like. I will only require you to know what I lecture on, and of course the application of the formulas. If we did something theoretical in class, of course you need to know that. But the idea is in the notes you actually see a derivation, geometric derivation of the area of this. We call this the frustum. It's like you basically take a cone and you chop off one end, so you get a drinking cup, so to speak, a round waste paper basket, so to speak. So when you talk about the frustum, again, think of it, as a truncated cone. That is, you have a slant height L. This is standard notation, and you have the lower portion and the upper portion that are both cross-sectional circles. So you think, okay, we have an R1 and an R2. So I say R1, R2 are radii of the circular ends. Now, this is what we actually derive in the notes, but it's a very useful formula when you think about it. If we let R be the average of the radii, the area of the frustum is actually very simple. You think it's similar to the area of the cone, but it's adjusted. So now, if we define R here to be the average of the two radii, we get the area of the frustum to be 2 pi RL. That is 2 pi times the average radius times the slant height. And so we use that average radius when we want to generate a definition for arc length. So here's what we want to do. How can this be helpful for us? Well, you're going to see all of this in this formula right here. What we want to do is to generate a surface by revolving a curve about an axis. So instead of revolving a region where we have a solid of revolution, we just want to generate a surface. It will still be a solid, but we want to focus on the C1 curve that would be revolved or rotated about an axis. And then it says the area of the resulting surface mimics the area of the frustum. So when you do this and you apply the partition of the integration set A to B, we'll do a little comparison here. Here's what's going on. We're thinking, how do we make this work with the integral? Well, L, or the slant height, is replaced with the element of arc length. So the little piece that we have over that particular subinterval. And then the distance to the axis of revolution is what we have here, the R, the average radius. So again, R, R, L, element of arc length. And then of course the 2 pi is just a factor. So if you remember the area of the frustum, that helps you remember the formula for the surface or the area of the surface. So again, the geometry and the calculus are married here like they have been from day one. That is, now we use the geometry of the truncated cone to evolve a formula for the area of a surface, whereby the surface is generated by revolving a curve about a specific axis. So remember, in the shell method, we have distance to the axis of revolution. We have the same thing here in the area formula. So again, R, R, L, element of arc length, 2 pi, 2 pi. And of course, if we have a different independent variable, we can change that out. Just remember, when you read the problem, think about it and just say, okay, well, here's my axis and I need this length. And so whatever variable that you utilize will be given by the problem. The problem will tell you what to do. And of course, if you start to work it out and it's awkward, then you may have to change the variable. So don't just assume that you're going to have to do something. Look at what you have and then make that determination. So now what we're seeing here is when we use the area formula. In this particular case, we do the same thing that we do for the arc length. We have to compute this unfortunate radical. So you apply the arc length technique. But since you have this R of X here, that usually means that this doesn't have to be very tidy, and this R of X will bail us out. That is, it will give us an integrand that's much easier than some of the ones we've done before that required extensive algebra. I'm not saying it's going to be, hugely simple, but usually this will make the computation of the indefinite integral or the antiderivative to compute the definite integral much easier. So let's apply that, okay? So the idea is we make these nice definitions using the calculus, and then we can do more fun problems. So let's start out with a reasonable WebAssign problem. So here we go. Let's look at actually exercise, because your problems are generated randomly, so the numbers don't always correspond. So for instance, here's what we have. We want to revolve y equals 2 times the square root of x. Okay, that's a nice plain Jane function, no problem with that. That's college algebra. For x living in the integration interval 4 to 9. About, we don't need about, we need about the x-axis. Now, again, WebAssign will be very tricky. They'll be very tricky at times. So remember, sometimes they'll say x-axis or they'll say y equals 0 just to trip you up. And they'll say y-axis or x equals 0 just to trip you up. So make sure that you interpret what they're saying correctly. It is so easy just to make assumptions, and I do it. And so when you all ask your questions, I usually know what to look for, because it is so easy just to think, oh, they mean this. And you really do have to read and reread to make sure. So be on the outlook for that. So what we want to do is compute the area of the surface. So in this particular case, if you think about it, the picture here is not required, but we like the picture just because it gives us a little bit of idea of what we need to do. So we'll just go ahead and do a plain Jane picture and not anything very elaborate. So for instance, we're going to go from 4 to 9, and we just got the plain old square root function times 2. So just draw a square root function like this. And we have a 4 to 9. So we don't have to have any scale here that's important. So we think about the curve here to here, this piece. That's the curve that we're actually, in this case, revolving about this axis. So now let's just remind ourselves that they use the uppercase S for area of a surface. Again, convention. Remember, we need 2 pi A to B, and then we have the average radius, the distance to the axis of revolution, and then of course we have we're using a Y here, the element of arc length. So what we have here, notice if we pick an X, we're revolving that little piece right there. So that is where the element of arc length comes in. And then of course, the distance to the axis of revolution in this case is just that of the function. So we just have 2 root X. So a lot of times, like when we did the shell method, the distance was just the independent variable. And so we don't really have to work very hard for this. The problem is tailor-made for this procedure. And so now we're thinking, okay, well, maybe this will bail us out, give us a simpler integral. So now let's go ahead and work with this, y prime. So just write y in a convenient way, 2x to the 1/2. So y prime in this case is just going to be 1/2, or 2 times 1/2, I'll work it out, x to the negative 1/2. So this just gives us 1 over x to the 1/2, if you like, just using the laws of exponents. Now, we square this and add to 1. That is the element of arc length requires that. So now 1 plus y prime squared will be 1 plus, I'll just go ahead and write it this way. I'll use the radical here just to give some practice. So you can square that in your head, but that'll just be 1 plus 1 over x. Now, of course, we want to make this a little bit tidy, so let's just go ahead and get a common denominator, if you like. So this will be x plus 1 over x, like that. So don't worry about the algebra. Work out the algebra, clean everything up. Usually a common denominator is preferred. It will help open the door to patterns that will help you out, okay? So now we can apply the square root and the formula. So we're good to go. We've done the hard part. So this, by definition, S will now be 2 pi. And then we have what? 4 to 9. Well, compared to the last problem, this is a walk in the park. You do some really tedious problems with new formulas and lots of logarithms, then you do this and it's very simple. So the more you challenge yourself, the better you get at this process. And so now notice we have r of x, the distance to the axis of revolution. So we have 2 square root x. And then now we have the square root of this. Remember, we have computed this, so we need the square root of this. So we see that this is a big help. Well, for what it's worth. So factor the 4 using the linearity of the integral. Oh boy, like I say, the arithmetic, if it's not the arithmetic, it's algebra. So now we'll use the identity here. This will be the square root of x times the square root of x plus 1 divided by x square root. Again, this is valid for all values of the variable for which it is defined. So we're good here. You know, we have to make sure that on this interval, this actually makes sense. And since we got 4 to 9, this identity is always defined on that interval. So we don't have to worry about any issues. We do have to think about it. So now the square roots absorb. You do have to think about what you do. I like your questions when you say, well, I worked with this and I'm not sure what to do next. That means I know you're thinking. So I appreciate that. And you just don't throw caution to the wind. So now we've got a easy chain rule problem, add 1, divide by the new power. So let me just go ahead and write this with the 1/2 power. So now chain rule says we can just, this is the u and there's the du. So we get 4 pi. So we're going to add 1 to get 3/2, divide by 3/2. That's multiplication by 2/3. So we have x plus 1 to the 3/2, 4 to 9. Again, very straightforward. And so now we have, in this case, we get an 8 pi over 3. And so if we substitute the 9 plus the 1, again, this is some easy arithmetic. We just get 10 to the 3/2. And then, of course, if we substitute the 4 here, we get 4 plus 1, which is a 5. So we get 5 to the 3/2. So we get 8 pi over 3. And then if you will, and this is up to you, you can write this as 10 times 10 to the 1/2 and just use the square root symbol. That's a standard procedure with these types of problems, but you don't have to do it. That's certainly fine the way I've written it there. Okay, so when we look at problems like this, what we're trying to see is, again, utilization of a definition. That is, as future engineers, computer scientists, math professors, whatever, you can design models and things to your choosing. And so you can, you know, you're making a model and so you want to utilize this formula. I mean, when you get to Cal 3, there'll be generalizations of this, but this is certainly a very efficient way to analyze a model that you may have created, just using techniques from your calculus classes. Okay, let's look at another example of this. Again, very straightforward here because we had the radical here, but notice that even without it, you know, we still have issues, but I'll just say this: formulas that are generated may be user-friendly or not. And as you get more and more complicated integrands, you have to investigate other techniques of integration. So that pretty much opens the door to that problem and why we're interested in doing it. So now let's look at another example of the area of a surface, and then we'll look at another example of an arc length now that your feet are wet with this. Now, here's what we want to do. This is a good example. It says compute the area of the segment of a sphere. So we're going to revolve part of a circular arc to get part of a sphere, so to speak. I'll say more about this. Compute the area of the segment of a sphere. So how are we going to do that? What we're going to do is revolve y, and here's an arc of a circle, 49 minus x squared raised to the 1/2 power for x between 0 and 6, not 0 to 7, we just want part of the arc, about the y-axis. And we'll do a little diagram here to make sense out of this. So we're thinking if we do something like this, we just get a cap, so to speak. The segment just generates a cap of the sphere. A segment, that's what the terminology is, segment. So now what I've written here, let's just pretend that we're doing the 7 to 7, and then we'll stop. So we've got the 7 here, and then I'll just kind of guesstimate a 6 here just so we get a picture. A scale's not exactly perfect. But for instance, we could think of just drawing a circular arc to here. But instead of continuing to this point, we're going to stop here. We're going to stop here, and so we're going to get a cap. We're not going to get even a hemisphere, and we're going to do the revolution, in this case, about the y-axis. Let me make that arrow a little better. Okay, so now when you think about this, you get like a little helmet, a little cap here. So for instance, the segment looks something like this. That would be a segment. Not the complete hemisphere. This is what we call the segment. And so now, when you think about this, if you look at this particular setup here, this is what we're interested in doing. For instance, now, let's do this. Let's just say y of 6. Y of 6 will be 49 minus 36, 1/2. But that's just what? 13, square root of 13, right? So here, we have square root 13, and we have what? 7. So I like to do things in a way that makes sense algebraically and geometrically. So now what we can do is, if we're revolving about the y-axis, we can just pick a y. So let y live here. So we'll pick a y, and then of course the distance here to the axis of revolution will be r of y. So let's go ahead and see what that is. It's easy to do. I mean, we just flip everything around. Notice that in this particular case, when we solve for x, this is symmetric in x and y. We have x of y is just 49 minus y squared to the 1/2. So that's what goes here. So when you look at this particular example and you think about it, you're like, okay, well, we've got this curve here that we're interested in, and we've got the distance to the axis of revolution. Now we've got to think about the formula. So now we've got what? 2 pi, and now I'm using y, so I'll just write a c and a d. We have r of y, and then we have the square root here. We have 1 plus x prime squared. Now we have x as the dependent, dy. So I think it's interesting to look at this problem in the other variable just for some practice. So now let's go ahead and work on this. We'll use our chain rule. So x prime, we want to construct this first. X prime will be 1/2. So the picture here just kind of organizes what we're doing, just to kind of give us a leg up on the organization. So we have 49 minus y squared, subtract 1 to the negative 1/2, and then the good old chain rule, negative 2y. So we've seen this before. So the 1/2 and the 2 absorb, and we get a negative y. We get 49 minus y squared to the negative 1/2. Or if you will, we can write it this way. So now let's go ahead and compute, in this case, the 1 plus x prime squared. So we get 1 plus negative y square root. Now, a lot of times you can do this in your head, but it's good to go ahead and write this out for now, just to have something to check. So this gives us 1 plus y squared divided by 49 minus y squared. So like I said before, go ahead and clean this up with a common denominator. 49 minus y squared. So we get 49 minus y squared plus y squared. And then the y squared is absorbed, and we get 49 square root 49 minus y squared. The idea here is that if you convert to another variable and you have very straightforward algebra, the key is that we're going to end up with an integrand that's really simple. So this is certainly worthwhile to do. And it's a way that makes sense, that's easy to teach. And so now, by definition, the area of the segment, the area of the surface, will be 2 pi square root 13 to 7. And now we have r of y, that's the square root function, 49 minus y squared. Then times, in this case, oh, and what I did here, and you all are thinking, Professor Ron, why did you go ahead and put that square root? Because I'm thinking down the road. I'm like, yeah, go ahead and tell them to square root, but don't square root the 49. Yeah, just leave it out for now. We can't turn our brains off quickly enough. Now we've got the argument of the radical, which we can now square root. So now this will give us a 7 over the square root, and the square roots will absorb. I'm just doing the extra steps here so you can see everything, and you can often leave out steps if you want. 7 over the radical. So we're left with a really simple integrand. So the radicals absorb, and so we have a 7 times a 2, so that'll be a 14 pi square root 13, 7 dy. And that's the easiest integral in the world, right? So this gives us 14 pi, and that's just a y, so we just get 7 minus square root 13. Because we just have y evaluated from 7 to root 13, so we just have the difference. So this is 14 pi times y root 13 to 7, which gives us this. So what I want to point out here is how you choose to set up the algebra usually should be in a method that's easy to actually compute. You can do other ways. You can change the problem around. Like I said before, you might find that using the shell method is better than the disk method, or the disk method is better than the shell. They may both work, but I have a problem written up in your notes where I say this was a lot of work. And so we would rather use a method that would allow us to have less computation to do. So when you do these types of problems, especially with arc length, and then of course the area of a surface that's generated by revolving a curve about a specific axis, we can utilize simple geometry here and see that we actually produce an integral that's trivial. But again, we just apply the formula and work it down piece by piece. And of course, if you have a little typo here, you think ahead and do too much too soon, you've got all of your steps written out here that can easily allow you to check what you're doing. Because again, you follow the formula, you follow what the mathematics tells you, and just work it out step by step, just like symbolic calculation. Okay, so what I want, again, the surface area formula will be generalized in Calculus 3. And so kind of look at this like, okay, kind of like the cross-section method in 7.2. It's a really interesting method, and it has more far-reaching consequences. But when we think about geometrically, I guess this is closest to the shell method, because remember, with the shell method, we always need the distance to the axis of revolution. That's a very nice method and fairly easy to articulate. Remember, we need the height or the length of the strip. So all of these techniques are related. So as you learn these, write these techniques down on note cards and practice. Just take out a clean sheet of paper and write everything down and get everything organized in your brain. I think that will be a helpful way to process things and get this into your long-term memory register. Now, what I want to do is go back to some of these examples here. I went through your WebAssign as I always do, because I'm the one that picks the problems. But I thought that we would do an interesting little example here. It's called the length of the asteroid. There's also a finding the area of the roof, which utilizes some exponentials. But I think I've done enough of that. You won't have any problem doing that. That uses a inverted Cantonary. So again, the hyperbolics are there, but you get integrals that you can actually do. Now, what I want to do here is a nice example from physics. This is called the length of the asteroid. The length of the asteroid. Now we have to use a little bit of care here. Asteroid. So that's an A. And we're given a Cartesian equation in this particular case. We have x to the 2/3 plus y to the 2/3 equals 4. So this has a lot of symmetry, x-axis, y-axis, origin. So lots of symmetry. Lots of symmetry. How many? A lot. A lot. It's too bad that's not one word. It's interesting. Our language is so useful, and we often have to remind ourselves what words actually mean, because we grow up hearing words and we assume we know the meanings, but maybe we've learned them incorrectly. So what we want to do is find the length of this, but I want to say a little bit about this curve. First, what I want to share with you is we want to think about how we can write this in one independent variable and then use some analysis. So first, I'm thinking, okay, we got all this nice symmetry here. So we get the little star shape. I'll show you what that looks like. We'll have y to the 2/3 equals 4 minus x to the 2/3. Now, this is basically the square root property. So this implies that y will equal plus or minus 4 minus x to the 2/3 to the 3/2 power. So we get two radicals here. Now, what I want to think about in this particular case is what's going on here. For instance, what do we have in terms of intercepts and things? So we're going to think this way. For instance, if y is equal to 0, what does that mean? We have, and we'll look at the, in this case, what do I want to do? I'll look at the upper arc, or in this particular case, looking at this. So we have 4 minus x to the 2/3, upper or lower arc, equals 0. So if y is 0, this argument must be 0. So this says x to the 2/3 equals 4. So x will be plus or minus 4 to the 3/2 power. So x equals, well, the square root of 4 is 2, you cube it, we get plus or minus 8. Okay, so that gives us some analysis here. Now, what I want to notice here that is with this equation, to make this doable, because this is not a trivial problem. Observe the graph is symmetric in the line y equal x. Obviously, if you replace x with y, you get the same equation. So this is like really, really important. So we can save ourselves some time. So for instance, if you think about this and you say, okay, well, what does that actually mean? Let's go ahead and draw what we have here. We have all these 8s running around. We've got the 8 here. We have the -8 here. And then the y and the x, they're symmetric. So we'll have 8s all over the place. So we get an 8 up here and a -8 down here. So that's going to be where we're going to do a little sketch. And so if we have symmetry in the line y equal x, we could say the following. That is, let me get the, let's see here. What do I want to say with this particular example? So if I do, okay. So if and only, if I've got a little argument here that I want to share with you that I think will make this a little bit simpler, but let me just make sure I'm going to state this correctly. So if I do this, let's see here, and I did that computation, so oh, okay, here we go. This is what I want to say. Take this here, and here replace. I do these in my head, and then I'm thinking I got to tell my students what I actually did. Replace y with x. So with that, right up here, we'll get 2 copies of x to the 2/3. So I just basically want to see when x is equal to y, what's the value down here? So we can get an interval of integration. So now we have x to the 2/3 plus x to the 2/3 equals 4. Okay? So now I got 2x to the 2/3 equals 4. So divide by 2, x to the 2/3 equals what? 2. So now square root property, x equals plus or minus 2 to the 3/2. Now that's not a pretty number, and I wrote here unfortunate number. So these aren't pretty numbers. They just kind of live the way they are. And so now I can go ahead here, and I'm just gonna mark off equidistant here. Get the line y equal x. So now when we come down here, we get 2 to the 3 halves. Okay, now what's interesting about this curve is that we get a 0 here, and we've got all of these x and y intercepts. But now what we're seeing, and we'll see this with the algebra here, with the derivative, we have what we call cusps here, where the derivative does not exist. And we'll see that when we actually differentiate. So you get something like this. You get the little star shape. And we've got symmetry with all the axes to here. Same here. Just this little simple analysis tells us that the curve has to look like this. And then the calculus will support it. Right there. Now, here's the point that we try to make with this. This is an elegant problem. Since we have this curve here, and I drew it kind of bad because I should have it running through here. I'm sorry, my curve is really lousily drawn. So let me make my picture better. I should have done this last. What is it? Live lecture, the best lecture there is. So now, there's my 2 2/3, or 3 halves, sorry. So that becomes our interval of integration. Now, if we look here, and all that, let me move this over. We got this piece and 8 of them from here to here. So this is 1/8 of the curve. 1/8 of the curve. So using the symmetry, we can integrate applying the arc length formula to here, and then just multiply the result by 8. So that will give us because we cannot mow over these places where the derivative doesn't exist. That's not going to work. That would give us just hash, as they say. So now, at least what we're seeing here is we have a method that will be supported by the geometry. So again, now, so this says use symmetry. This is fun. This is really important right here. That's what gives us this. And again, that takes a little understanding of the fact that you've got all this beautiful symmetry with this curve via the equation, the Cartesian equation. Cartesian equations are not always, you know, horrible. Some of them really are, but we're happy that we have this. So now what we're going to do, this implies that if we go up here, we're going to focus on this particular arc here from 2 to the 3 halves to 8. So we'll say y lives here, excuse me, x. And then I'll get my y curve. So we have x lives between 2 to the 3 halves to 8. And then we'll take the positive curve, y equals 4 minus x to the 2/3 raised to the 3 halves. So now we have this interval of integration, and we have this function whose length we need to figure out. This function is that blue thing right there. So the reason I wanted to save this for last, we don't have any fancy hyperbolic functions. We don't have, you know, to worry about things that may or may not be rusty. This is just plain old algebra. And the thing is, this art has been lost in our mathematics curriculum. I teach this in this class because I know you don't get this in high school anymore. So that's why we're doing it. So now, notice by definition, well, let's not be so quick here. Let's go ahead and build all of this. Let's do y prime. So we have 3/2. 4 minus x to the 2/3. Subtract 1, we get a 1/2. And then we want to multiply by the derivative. So we get net chain rule, negative 2/3 x to the negative 1/3. So notice the 3/2 and the 2/3 absorb. So we get the negative 4 minus x to the 2/3 to the 1/2 and x to the 1/3 downstairs. Now, again, this is nice and user friendly. So now what we want to do is add 1, square this and add 1. So remember, arc length, a to b, square root 1 plus y prime squared dx. All this is relative to x. Now we could have used y. There's nothing sacred about this. We could have solved for x here, but you know, let's just stick with what we're most comfortable with. That's not a problem. So now 1 plus y prime squared will be 1 plus, so we'll square this out. That'll absorb the negative. So let me just write this out. Negative 4 minus x to the 2/3 So when we square this, we'll get 1 plus 4 minus x to the 2/3. And then, of course, x to the 2/3 here. So again, we relieve ourselves of this radical. And then, of course, we square this using the identity laws of exponents. Now let's get a common denominator. So this is the same thing. What you're seeing is that the techniques are starting to be repetitive. So now we get x to the 2/3 plus 4 minus x to the 2/3. And let's see here. So that doesn't leave us a whole lot. I thought I'd lost everything, but I didn't. I've got enough. 4 over x to the 2/3. I thought, where's my content going? I don't have any content left. There we go, right there. Now you're thinking, is this not a miracle? We have what is appearing to be a rather complicated curve, though simple, based upon the symmetry. But then once we do our due diligence here, we get something that we can easily square root. So now by definition, S will be the integral. Now our interval here is 2 to the 3/2 to 8. And then we take the square root of this. So we get 2 to the 3/2, 8. So that'll leave us with 2 divided by 8 to the 1/3, using the laws of exponents, our identity, dx. So now let's write this in a user-friendly way. So we get 2 integral 2 to the 3/2, 8 x to the negative 1/3 dx. So, oh, and of course here, use symmetry. So we need 8 times this. Remember, we only have 1/8 of the curve, so symmetry. So now, what does this give us? This will give us 16. So add 1, divide by the new power. That'll give us what, a 2/3. So 3/2 x to the 2/3, 2 to the 3/2, 8. Amazing. We've reduced this to just simple arithmetic. So now we've got a 2, so that's what, a 24. So we have, what do we have? 8, so we get 8 to the 2/3 minus 2 to the 3/2 to the 2/3. So what's nice about this is that we have reduced this problem to a simple calculus 1 integral. But again, you could have done this in calculus 1. You could have done this problem in calculus 1. But for some reason, we wait to calculus 2 for this. No reason really, but I guess you do need to learn the basics first and get all the integration processes done with the differentiation and all. But this would certainly be done with calculus 1 techniques because that's all we've used. So now we've got 24. And so this will give us 8 to the 2/3. The cube root of 8 is 2. And then 2 squared is 4, last time I checked. And then here, these absorb. So we just get 2. So 3/2 times 2/3. So this is 2 to the first power. So we get 24 times 2, which is what? 48. So, and in my notes here, and of course, every time I write these problems up, I always think to myself, well, this is a good problem. Well, ladies and gentlemen, in general, any math problem is a good problem. Time rate distance problems and fraction of work problems in pre-calculus with lots of number theory with AC methods, Professor Ron's AC method, are elegant problems and hard to do because if you don't look at factors correctly, you can miss a factorization, and sometimes you just have to break it up, do the prime factors, and mix and match. The idea is when we look at this particular problem, we think of the fact that the Cartesian manifestation here is not half bad because it showcases all the nice symmetry that we have. And the main thing, again, this part, just the square root property, we're fine with. We have an upper arc and a lower arc. That's simple. But when we think of the symmetry with respect to the line y equal x, we just want to figure out where do these intersect, because with this nice symmetry, we can then from here get a nice interval of integration and focus on 1/8 of the curve. The only thing we have to remember is once we do the due diligence, we have to make sure to remember the 8 here, kind of like when we did the torus and other problems where we have used symmetry. The beauty of the symmetry is that it appeals to us when we think about it, but once we finish all of the work and we set up the integral, it's easy to leave out. So be very careful of that, especially when you're doing your WebAssign kind of thing. But what I want to do now is help to set up the problem about the area for the roof. Let me find that. And this is a good problem. I'll go through this. I'll summarize this one. Let's see here. So know how to do this. Know how to do every problem I do. But you should master this. Master this technique. Teach your friends. Okay. The idea here is that where have we used calculus? Well, all of this is involving the formula for the arc length. But where do we actually do calculus? Okay, right here. I mean, when we go from here, I'll get to this point. This is algebra. We're using properties of the definite integral right here. This is the calculus part right here. Getting ready for that is all college algebra. So again, you don't leave anything behind. When you take the calculus, you bring everything with you. And we all know that when you're thinking about the calculus, it's not the calculus that's the problem. I had an argument with a teacher, a high school teacher one day, who was saying, "Oh, well, it's the concept that's so hard." I said I disagree. I said most students are vastly intuitive about the concepts. It's the mechanical part. And then after a certain while, we both agree that yeah, the concepts can be abstract at first, but the student has no problem understanding what to do. It's just driving through the mechanics, which has to integrate nicely with the concept. Now, I want to look at this example that I wrote up here, and I want to just kind of summarize it in the end. to show you some points of it. Now, this is from your WebAssign, and basically what we have is a barn is 100 feet long and 40 feet wide. It says a cross section of the roof is an inverted catenary. For instance, if you look at power grids, you've got two steel power poles, and you've got an electric line running between them. The curve that's generated by that electric line is a catenary. Okay, that's just the physics of the situation. And so you see catenaries every time you see power lines draped between two poles. So the inverted catenary has this shape. That is, what happens here is that if you look at this, that's just basically the hyperbolic cosine, except for the 1/2. E to the something plus e to the negative something divided by 2. There's no 2 there. But what they've done is they've used some college algebra. They stretched it vertically. Then they reflect it in the x-axis, and then they do an upward v-shift by 31. So this is college algebra here. So the catenary, which usually runs like this, is now like this. And that's what you get. You get a roof that has the shape of an inverted catenary. So again, that's the shape you would see when you have the lines between two poles, but again, inverted. So again, think of the analogy with the electric lines. Now, what we want to do in this particular case is find the area of the roof. So all we need to do is to compute the length here that I've marked out in red, and this is what the problem does. It gives you a nice interval of integration because the exact is a little bit messy. So what they say is we want to do is to compute the length of the inverted catenary and then multiply the result by 100 to get the area of the roof. So this is what I wanted to do for you, just to kind of summarize. So notice this problem is set up. This was not like the last problem where we had to work really hard to set it up. So what I want to do is go through some of the algebra here. Now, first, what we do is we take this function and we remember that we need to differentiate. So of course, that's 0. So what we have in this particular case are derivatives of exponentials. So we just multiply via the chain rule, this term by 1/20 and this term by a negative 1/20, and we get this. Now, what we want to do is to square the derivative and then add 1. So when we square the derivative here, we're going to get the 1/4 here, and then we square this term. That'll absorb one of the 2's here, giving us x/10. Again, squaring this will absorb one of the 2's in the 20, giving us negative x/10. And then, of course, this times this is -1 hit with the 2 because these are just multiplicative reciprocals. So, or multiplicative inverses. And so we get a -2. Now, of course, we get a common denominator here. Same old song and dance. We get the common denominator here of 4. So this brings the 4 over. So we have the e exponential term here, the negative exponential here in the power, as I'm referring to, and then the -2. And now, of course, we have a perfect square again. We have e to the x/10 plus 2 plus e to the negative x/10. So now what we can do is just let uppercase A, in this case, be e to the x/20, and the uppercase B be e to the negative x/20. So when we square both of these, we get the x/10 powers. And then, of course, when we multiply and hit with a 2, we get the 2 there. So this is a beautiful perfect square. So what I wanted to impress upon you is that this problem is actually easier than the other ones we've done. It just looks menacing because you've got all of these fancy words here. But just think about the power lines. So now to finish, this is really simple. So what I've tried to do today is impress upon you that you really know how to do all of this. You just have to put the basic ideas together. So now we've got this beautiful integrand we can square root. Now, notice here, and you're thinking, I could have used some symmetry in some of these cases, but I went ahead and worked it out. This integrand here is actually even, so I could have used symmetry, but for some reason I just mowed through it. But we'll do it. You can use symmetry if you like. I just noticed that when I looked through my calculation. So we take the square root of this. That is, remember, S will be a to b square root 1 plus y prime squared dx. And so we take the square root of this, which is a nice even function. So again, you can use symmetry when you write this up. I did too much work. So we are relieved of the radical, nice positive function. This is basically the hyperbolic cosine. It's exactly the hyperbolic cosine, which is an even function. So at this point, you could do 0 to 20 and have the 2 here, which would have made this a lot easier. So now notice we factor the 2 here, and then we just evaluate. And I think because this is so easy, I didn't bother to do it, but I would do it just looking at what I've done. So we evaluate here the antiderivatives in this particular case. Let me just say this: when you look at both of these, what you want to do is you've got this factor here, 1 over 20. So when you do, let me give you a little key here. When you do e to the kx dx, this will just be 1 over k e to the kx dx plus a constant. There's our formula there. And so notice here, the k is 1 over 20. So now we have the 20 here. So 1 over 20 is 20. So I have the 20, the 1 over k, which you see there. So that's the formula I've used there, which is just taking the derivative backwards. So we get the 20 over 2, and we evaluate here. So now you can see that I did waste a little bit of time not using the symmetry. So we replace with 20, and we'll get e to the 1 and e to the negative 1 in difference. And then minus, replace with the negative 20, we get e to the negative 1 minus e to the 1. And now what we can see here is everything pretty much adds together, so to speak. We have, in this particular case, we have, let's see, what do we have here? We've got the plus e here. We've got 2 copies here and 2 copies here. So notice, let me write this down so you can see it. This gives us 2e, and this gives us minus 2 times 1 over e. So now you can factor the 2 here, and that'll give us a 2 times 10, which is a 20, e minus 1 over e. So again, when you're working on this, if you like, go ahead and use the symmetry. I just mowed over that, which I don't think I should have done, but I'm noticing that. So now the roof area in this case will simply be the arc length, which we have computed exactly, times 100. So we have 100 times 20 times e minus 1 over e. So that's exact. Now, if WebAssign asks you to approximate this, then fine, you can approximate the exact answer. So again, just remember in this case, let me write this in. At this point, use symmetry if you like. Use symmetry if you like. So what I wanted to impress upon you today, you may not have seen too much with the hyperbolic functions in Calculus 1. Like I say, that's at the end of Calculus 1 when I teach the course to give the basics, because it's like I keep saying, most of you will be future engineers. You will have an intimate relationship with the hyperbolic functions because they exist all over the place. So what I want to focus on, or to summarize today, is that we have these really nice formulas here that we've used. That is, we have the formula for the arc length, which again requires computing the 1 plus the y prime squared, manifesting that in a very convenient algebraic way, and then passing to the integral, and of course, using whatever symmetry, which I should have used there. And then we have, in this particular case, utilizing the area of a frustum to generate a formula for the area of a surface. So when we look at this, we basically see these are connected, this reminding us of the shell method. So when you work through these problems, again, when we have our test next week, the topics will stop with today. Anything that we do next week will just be new material, and that'll be on the second test. So as you work through your problems in the shell method, some of you have already probably finished the shell method since we did that last week. As you work through these problems, go back and see how they interrelate with the problems you've already done. And you're going to find that the earlier section problems are simple because this combines all of the techniques that you have to do. So I wanted to make sure that you were aware of the hyperbolic functions. So when you do these examples, apply the techniques that I have shown you and be vigilant about the algebra and master the asteroid problem. I think that's a really, really beautiful example. It's a curve theory example, and you will see that later. A lot of you in physics and a lot of you may be in a differential geometry class that you may take at the university. So later on in the week, I'll have some more information about the upcoming test, and that will be on Blackboard. So you'll have a nice window of time to do it. And I'll give you all the information that you need to know about it. And I'll also talk about the class time that normally you will take a class time to give the test if we were doing face-to-face. So I may just have that be as a free day. I'll have to come up with that, make some decision as to what I want to do with that time. You may need the time to rest and to focus on taking your test. But I appreciate your attendance today. Enjoy this material. Once we finish the work applications and then the center of mass applications, we'll move on to reviewing some integration techniques and some new techniques of integration that I think you'll find very interesting. But get some rest, enjoy your day, and enjoy doing your mathematics. Everybody have a good day.
Thank you. Have a great day.
You too. I appreciate your comments. Thank you, everyone. And when I say X lives here, I'm basically saying where does X live in terms of a set? I think that's just a Southern colloquialism that I developed when I was an undergraduate at Carolina. But everybody, again, enjoy doing these problems. It'll make you better at your Calculus 1 techniques. So bye.